Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good Better Best Online Videos for more video content. Alright, hello grade 10s, formally. What we're going to do now is we've entered into the phase of revision for our year, okay, because we have actually gone through all of the content for this year. Wave, sound, and light, according to our little document or our guidelines for the topics that needed to have been taught, have already been covered. And we've covered a lot in detail. We even spent a lot of time, or more time, on some topics than others. So we gave a lot of time to every single topic in great detail. So the only thing left now is to obviously revise everything that we have done topic for topic in this year. We'll start by having a look at, before we go through certain topics, we'll start by having a look at an entire exam paper. We'll start with paper 2 and then we'll move on to paper 1. We'll take you through an entire November exam. Okay, now this November exam here is the 2015 common paper, so that's about 6 years ago. It's 150 marks for 2 hours. Okay, and we're going to skip the multiple choice and go straight to question 2. Okay, so question 2, we'll actually do this together. Okay, so I won't give you or I'll decide which questions maybe I'll give you to do on your own, if I decide to do that at all. But I'll be mainly looking to do these questions with you guys. Okay, so question 2 here of this paper says start on a new page. Okay, very important. Start each question on a new page. Get into that habit, because with grade 12 they're going to require you to start each question on a new page. Alright, so grade 10 learners were given the substances in the table below. Okay, we've got brass, copper, sand, pure air, oxygen gas, salt solution, sugar, table salt, carbon dioxide, and magnesium oxide. Now from the table above, write down, and they give us a list of what they're looking for. 2.1.1, the first question, write down an element. Now there's more than one. Okay, you can choose any one here. Okay, there's more than one, you can choose any one. Okay, so for an element, I see there is oxygen gas, that's an element, as well as copper. In other words, we find copper and oxygen, we find them as an element on the periodic table. Okay, so you can choose any one of those. 2.1.1, I'm going to choose copper, because I think oxygen gas is going to be used again. And homogeneous mixture. Alright, we've gone through what homogeneous and heterogeneous is. Okay, homogeneous mixture of one kind. Okay, and we're going to have a look. There's more than one as well. There's salt solution, that's an homogeneous mixture. Pure air also is an homogeneous mixture, as well as brass, if you didn't know. So you can write down, of course, any one of these. I'm going to write down salt solution, which is just salt and water. 2.1.3 says a diatomic gas. In other words, diatomic, it's combustible. All right, so that's oxygen gas. You know, if you open up an oxygen tank, pure oxygen tank, over a flame, it's going to ignite the flame, or cause the flame to be a big flame. Right. 2.1.4, a compound which is a solid at 25 degrees Celsius. Okay, now there's more than one here, which I'll also write down all three in case you didn't know. Magnesium oxide is a solid at 25 degrees Celsius. Okay, table salt. Now 25 degrees Celsius is roughly room temperature. Okay, roughly room temperature. as well as sugar. Okay, so they threw you off there a bit with the 25 degrees Celsius, but 25 degrees Celsius is roughly room temperature. So table salt and sugar obviously are solids at room temperature. We would know this because we have them in our cupboards. And obviously we use the salt shaker when we need to obviously spice up our food a little bit or flavor our food, and sugar when we want to sweeten our tea or our coffee. And they are still quite solid at those temperature. They don't melt. They're not liquid or syrupy or whatever you want to call it. 2.1.5, a heterogeneous mixture. Okay, there's only one here, and that is sand. Okay, sand is a mixture of all different kinds of grains. Okay, go to the beach, some grains are darker than others, etc., etc. So, and that's natural sand, of course. So sand is a heterogeneous mixture. Okay, and that was this little question 2.1, just using the table. Okay, some stuff we didn't use, of course. Okay, cool. Let's have a look at 2.2. Now, 2.2 says the learners perform an experiment to separate a mixture of sand and sugar. Okay, the experiment is done in 3 steps as shown in the diagrams below. Okay, so let's have a look here. Glass rod, we've got water there, sand and sugar is looks like it's thrown into there, and then we've got solid X, mixture Y, step 2, and then we got H2O gas, which you can see first was a liquid in step 1 and now is a gas in step 3, and mixture Y stays behind. Okay, now we got to have a look at what is all these steps and have a look at X and Y, what it is, etc. Okay, so 2.1.1a, write down the process that is illustrated in step 2. Okay, now judging by the apparatus that is used there, it's definitely a process called filtration. So 2.1, and this is A, I think. This is filtration, which we have gone through in previous sessions. Okay, here we go. B, I think, was the process illustrated in step 3. Step 3 is evaporation. Whenever we see water leaving in a form of in gas form, we know that's water vapor. Okay. C, asked for solid X. All right, solid X would definitely be your sand. And then D, oh, let's go here. D is mixture Y. Well, mixture Y would definitely be your sugar solution. In other words, your sugar that is dissolved in water, sugar solution. Okay, and then of course, if you want to, then the evaporation process in step 3 will obviously cause the sugar to be left behind. Okay, and that was 2.2.1. 2.2.2 says, is step 3 is step 3 a chemical or physical process? Give a reason for the answer. Well, step 3, the answer here, if I can just switch up the tabs or the layers here as well. Let's come to the top here. 2.2.2. This is definitely a physical process, and let's explain why. It's a physical process because there is no new substance that is formed. Okay, no new substance that is formed. Okay, because water only changes phase. Okay, water only changes its phase from liquid to gas, so there's no new substance formed. We're still left with sugar. We haven't formed gold. All right, we haven't formed anything else, or pure soil or anything like that. We haven't formed compost or whatever. No new substance is formed. We're still left with what the substances that we had at the beginning. All right, except that water just changed its phase. The sugar, still sugar there in its entirety after water has left the solution. Okay, we still get left with sugar. All right, the same sugar that was used in the beginning. Sorry, don't know why I said that. Okay, so it's a physical process because there's no new substance that is formed as water just changed the phase. You could have also said that water only changes phase. Okay, I like this answer though. No new substance or substances are formed or formed. Okay, we can take it to question 3. Now remember, this is 2015 papers, relatively old paper. Sometimes the question structure might have changed, but not that much, so we can still use it. Okay, now question 3. The table below shows boiling and melting points of substances A to D, and both in Celsius. And they want us to now, obviously, one of the first questions for almost any question or section in physics is to define the term boiling point. Okay, so 3.1, or define a certain term. So if you want to define the term boiling point, first of all, things that you need to mention first is the temperature, all right, at which water vapor, or maybe vapor pressure. Let's not say water vapor because we don't just need to boil water. So at which vapor pressure is equal up to the external or atmospheric pressure. Okay, and of course a phase change will happen in boiling point, usually, as we see with water. Okay, let's go to 3.1.2. That's the I would argue or advocate rather for this one, equal to the atmospheric pressure than say external pressure. Okay, that's just my piece of advice there. From the table above, write down the letter either A to D that represents the substance which is a liquid at 100 degrees Celsius, a solid at 100 degrees Celsius, and a gas at 25 degrees Celsius. Okay. What we've got to do here is analyze the boiling point and melting points. Okay, so boiling point here we can see is, let's just work up the table, is about 184 degrees Celsius. And its melting point is at about 90 degrees Celsius. Alright, so let's see. Over here, there's minuses over here. So boiling point is at minus 188, and the melting point is at minus 220 for substance C. And then for substance B, we've got boiling point at 444 degrees, which is extremely hot, and then melting point at 133. Okay, so this is what I'm going to say for A. We can see, for 3.1.2A, a liquid at 100 degrees Celsius, that definitely must be D, judging by these 2 points here, these 2 temperatures. A liquid at 100. If boiling point is at 184, it must be obviously at 100 degrees, it must still be a liquid. And melting point is at 90, which is just 10 below. Okay, so 3.1.2A, I'm going to say that's D. I'll keep red for now. B, they want to know what is a solid at 100 degrees Celsius. Well, if melting point is 133, then I think a solid is definitely substance B. When the temperature is 100 degrees Celsius, it must still be solid if melting point is only at 133. So I'm going to go substance B for B. And then substance C, or for question C, a gas at 25 degrees Celsius. Well, that definitely, we've looked at, okay, we've taken B off the list, we've taken D off the list, we left with A and C. Now, boiling point is at 78 degrees here. That's boiling point. Alright, so boiling point obviously would be where there's a phase change either from liquid to gas. So it can't be substance A. I think it's definitely substance C by trial and error, because I got rid of A, so I'm left with none other than C, and I've used the others. So that's how I derived at that answer. Alright. So that was 3.1.2. Right. 3.1.3. Of course, they ask us now, which of the following diagrams represent particle arrangement of substance A? At 120 degrees Celsius, write down only I, double I, or triple I, which in Roman numeral for 1, 2, or 3. So substance A is boiling point at 78, but multipoint is at minus 117 degrees Celsius. So they want to know for the particle arrangement of at 120 degrees Celsius, write down only 1, 2, or 3. Let's see. Alright, so we need to have a look for substance A. If boiling point is at 78, then substance A at 120 degrees Celsius. Let's see. I think it must be I. Alright. Just the first one. So I'm going to go with that one. 3.1.3. First one I, which looks like the particle arrangements are still quite tightly compacted to each other, or with each other. Okay, next question. It's on the next page. The heating curve of a substance is shown below. 3.2. We've got temperature. This is time in minutes. So let's just analyze the graph quickly. We've got an upward slope graph from 0 to 5 minutes. 5 to 10, nothing happens. And then at about, let's see, 1, 2, 3, 4. So maybe, not sure what was the interval here necessarily, because that's 0, 5, 10, 15. So maybe halfway of this must be about 12. Anyway, but slightly maybe just before 11 minutes. Then of course there is a then the graph shoots back up again. Alright, up until here, in between 15 and 20. Then at 20, of course, it's still straight, nothing's happening. And then at 25 minutes, of course, it looks like the reaction stops, but it increases though, but it stops. Alright. Okay, cool. 3.2.1, write down the physical state of the substance at 15 minutes. Okay, well, at 15 minutes, let's see, there's still a phase change happening here. So, I think it's a liquid. So, I'm going to write that down. 3.2.1, so that's definitely a liquid. Okay, 3.2.2 says, what's the boiling point of the substance? Okay, boiling point of the substance. Okay, this is a little bit difficult right now, so let me see if I can increase it maybe slightly. Okay, the interval looks like it's there. They come in about 40s. Okay, so I kind of got to work out the interval here. Let me see, maybe that line is 130, 140. No, it's not. So 1, 2. So okay, let me just take a break to figure this out. So the intervals here are definitely in 4s. Okay, so one let's have a look here. 120, 124, 128, 132 is roughly about here. We see this a solid line, and then boom, it takes off all the way until about just under 160. So that's 160 top temperature there. 160 minus 8. We just see quickly. We got about 152 is the top temperature, but boiling point is definitely roughly around over here. So we got a boiling point for this question. Let's just zoom out a bit. What is the boiling point of the substance? It is definitely 132, which is roughly around this solid line here before it takes off here. The boiling point of the substance is at about 132 degrees Celsius. Also, because we can, sorry, just adding a Celsius here, 132 degrees Celsius. Because we can see, of course, this long line here all the way up until here. Okay, so that's definitely the boiling point there. Okay. Cool. There we go. Okay, 3.2.3, how will the average kinetic energy of the particles, get this down here, how will the average kinetic energy of the particles of the substance be affected, all right, between t equals 0 minutes and t equals 5, so between here, okay, we only need to write down increase, decrease, or remain the same. Okay, so we can see definitely there's an upward sloping curve from t equals 0 minutes to t equals 5 minutes. It's an upward sloping curve, so that means the average kinetic energy must be increasing. So for 3.2.3a, we know that's definitely increase. We only have to write down increase. Okay, or is it increases? Yes, increases. Make sure you stick with what they want you to write. Don't write increasing. They might mark it wrong. People can be funny sometimes. And then between t equals 5 to t equals 10 minutes. So we can see the average kinetic energy from 5 to 10 is a flat curve. All right. In other words, there's no change. So we write down remains the same. That should be quite intuitive and quite vivid enough. Remains the same. Okay, let's go back there. So we can definitely see that that is remains the same. All right, 3.2.4, refer to the kinetic molecular theory to fully explain your answers to 3.2.3 B. Okay, well, that's easy. The kinetic molecular theory says, well, not that it says, but I mean, it's, well, I don't know why that scrolled down, sorry. But basically, we know that heat energy is used to break forces between particles. Okay, so if we know that heat energy is used, well, let's write that properly, to break down bonds, break down, or we could just say break forces between particles. All right, if it's used to break forces between particles, it's used to obviously result a phase change. Okay, when those particles are broken, obviously, or forces are broken between particles, resulting in a phase change. Okay, it results in a phase change, right? What heat energy? Let's actually write that down. Heat energy does not change the speed at which particles move. So in the graph from 5 to 10, which is 3.2.3b, we can see that the temperature remains constant. All right, so that looks like it is at about just before we get 40, so that's probably about 24, 20, no, that's probably, let me see, 4, 8, 12, 16, 20, 24, 28, that's probably just at about 32, all right, 32 degrees Celsius for 5 minutes, or for about 6 minutes as it seems, it stays the same. So in other words, the temperature does not change. There's no phase change, all right? And the particles, or maybe for 5 to 10 minutes at 32 degrees Celsius, the particles are still being broken before, or the forces between those particles are still being broken. And then the phase change only occurs at about 11 minutes, maybe. roughly, or just before 11 minutes, or just after 10 minutes. Okay, at about 10.5 minutes maybe. Okay, so that's what we can definitely see there. And that was 13 marks. This question was about 13 marks, just reading off a graph, and the second part, the first half, reading things off a table here. So this was investigative questions for question 3. Okay. However, question 4, then it starts getting a bit more mainstream. Okay, with metals and non-metals, Lewis structure, stuff we're all quite used to knowing. Okay, so now that they've tested our memory and kind of made our brain work a little bit, hopefully they've opened it up a bit, so we can, of course, answer the next upcoming questions. Okay, cool. So let's go for question 4. Okay, now chlorine is a non-metallic element with an atomic number of 17. Okay, of course, when you be doing this paper, you'll have your periodic table with you. Now it has atomic number of 17 and can exist in isotopes. Okay, so define the term atomic number as well as define the term isotope. Okay, now isotope you're usually concerned with only in grade 12 when we do organic chemistry. Okay, and I'm not sure if we have touched on that term in this year's syllabus. Okay, but I will share it with you. That's a nice thing about past papers, is even if you don't learn something for the current year, at least you'll be able to learn something that could possibly that you could keep possibly at the back of your brain and take it forward all the way through into the future grades. So let's define that term atomic number, which is something that we have learned this year. Okay, so this is question 4, so let's just call it Q4. 4.1.1, I think it is. Yes, atomic number. Well, atomic number is, of course, the number of protons in the nucleus of an atom. Cool. And then 4.1.2, which I'm not sure if you need to know this year because I haven't come across it in the syllabus, but isotopes, okay, this is an atom or atoms of the same element having the same number of protons, but different number of neutrons. All right. Or another way to put that is atoms of the same element with the same atomic number but different mass number. In other words, they have different mass numbers. They don't have the same mass number. Okay. Right. Cool beans. Let's check out the next question there. 4.2.2. All right. They say that natural chlorine consists of chlorine 35 and chlorine 37. Okay. Write down the SP notation of chlorine 37. Okay. So this is a good example of isotope. Okay. They have the same atomic number, but they have different mass numbers. Okay. Now, atomic numbers of chlorine are the same, but you can see they have different atomic masses there. One is 35 and one is 37. Okay. So the SP notation of Cl37, this is 4.2.1. Okay. So that'll be 1s2. First orbital, it's got 2 electrons. 2s2, second orbital has also got 2 electrons. Okay, the s orbital, and then the p orbital, all right, has got 6. We move it to the third. S orbital has got another 2 electrons there, and then the third p orbital can only fill with about 5. All right, 5, 6, 7. That's 13. 8, 9. 2, 3, 2, 4. Am I right? Yeah, let's check. That's 6. Yeah. So 2, 4, 10, 12, and 17. Okay, is orbital. Okay, that's the SP notation. okay, which definitely will be a topic that we will be revising, okay, for grade 10. So not to worry, we will be revising those two notations, and we'll aim to explain it in detail, as not everybody was here when I did that lesson. Okay. However, it is on the YouTube channel, so just check it out. Okay, and we'll probably make reference to it as well. They want to know the relative atomic mass of chlorine. Oh, they say now the relative atomic mass of chlorine is 35.5 or 35,5. Write down the percentage of chlorine 35 in natural chlorine. Okay, so there's more than one way to do this, but I'm going to do the one that's obviously the most simple to possibly understand. Okay, so let's do it like this. So let's say the percentage of chlorine 35 is equal to X, and percentage of chlorine 37 is equal to Y. Now, obviously percentage, they both must equal 100. So let's say, well, X plus Y must give me 100. That's fair, right? Now, of course, this is maybe equation 1. For equation 2, 35.5, which is the atomic mass, must obviously equal to X, which is percentage of chlorine 35, plus Y, which is exactly what that is, 37, divided by 100 will give me obviously the percentage. Okay, that will obviously give me the percentage. Okay, cool. But we got to sub 1 into 2. Okay, so we got X plus Y is equal to 100, but therefore, if we want to get one of these variables, okay, we'll get that Y is equal to 100 minus X. Okay, so let's take this. This is the actual first equation. Let's actually take this and sub it in for Y, since we got a variable for Y. So let's come over here. Let's take it all the way to the top here. So let's take, well, 35.5 is going to equal X 35, okay, plus 100 minus X times 37. Now if we do that, we're going to get sorry, let's not forget divided by 100. So let's times 100 on both sides. Okay, we'll get 3,550 is equal to, well, 35x, okay, plus 3,700, which is 37 times 100 minus 37 x, of course. Okay, so let's see, we can obviously take him over here. So 3,550 minus 3,700, we're going to get obviously minus 150, and 35 minus 37 is going to give minus 2x, and we want what x is equal to, so therefore x is going to equal 150 divided by minus 2, x is going to equal 75 as our answer. And the question was, the relative atomic mass of chlorine is 35.5, calculate the percentage of chlorine 35 in natural chlorine, and we calculated that percentage to be, well, x to be 75, all right, as our answer. Okay, this one was a bit of a stinky question though, I will deny, but at least we know how to do it now and how to approach this question when it comes up in our papers. Okay, cool. Oh, sorry, there we go. Okay, question 4.3 says chlorine gas Cl2 consists of molecules. 4.3, first thing they want you to do is write down the number of valence electrons in a chlorine atom. then the type of bonding in chlorine molecules, and then of course the Lewis structure for the chlorine molecules. Okay. Right, let's see how we can do this. 4.3.1. Okay, let's maybe see if we can start 4.3.1 here. Okay, so remember the number of valence electrons in a chlorine atom. So we need to have a periodic table open for this. So let's maybe see if we can just access the periodic table here in this exam paper. Right, here we go. Let's find chlorine. Alright, there we go. You see it's in group 7. So the number of valence electrons, alright, in the shell there is definitely 7. So we're going to write down 7. Okay, it's old group 17, new group 7. So this one, here we go. So for that question there, number of valence electrons in the chlorine atom, it is 7. Okay, and I showed you guys how to do that now. 4.3.2, the type of bonding in chlorine, okay, you should know from my notes previously, is it is covalent. It's a covalent bond. And then 4.3.3, I ask us to draw the Lewis structure of chlorine gas. Okay, now I'm going to write Cl like this in white, and I'm going to draw the bonds in a different color. You won't do this. Okay, so remember, chlorine has 7, but there are 3 lone pairs and only 1 pair that makes the bond on each. So that little bond here is in the middle, and then there's lone pairs. So that's 1 pair, that's 1 pair, and that's another pair. So there's 1, 2, 3 lone pairs plus the one that can bond, all right, on either one. So there's the other lone pair, and lone pair. So there's 6 electrons that 6 valence electrons that don't do any bonding. All right, cool. But 1 on each does. That's why we have Cl2, why they can bond to themselves, because they can share this little bond here, because they both have 1 bond or 1 arm free that they can make. Okay, so let's just take away those dotted lines, and that's the Lewis structure. That was a very easy 2 marks there. Right, 4.4. Now, calcium reacts with chlorine to form calcium chloride. They want us to draw the Aufbau diagram for a calcium ion. So we go over here, we find calcium. Calcium over there is in group 2, all right, and we know its atomic number of 20, and it has a relative atomic mass of about 40, electron negativity of about 1. Okay, so let me just check something quickly. All right, cool. Got that. Okay, cool. So let's have a look at the question I think they want us to do for calcium is the Aufbau diagram. I think I might have just mentioned that before I went over onto this question. Just find out where. There we go. There we are. Draw an Aufbau diagram for the calcium ion. Okay, so if you're going to draw an Aufbau diagram, I need a fresh page for it. Okay, cool. So, of course, you got an Aufbau diagram. Let's start it over here. There you go. And then you got the second orbital up here. And then you got 1, 2, I think you got 3 here. And then, of course, you got 1 up top here. And then you got another 1, 2, and 3. Okay. So, let's fill them up. So the first one we fill up 1, 2 like that, 3, 4 like that, and then we fill up here 1, 2, 3, and then we fill up the other one, right, like that. So in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, then we fill up the third s orbital, 1, 2, and then we fill it up again with the p orbital. 1, 2, 3, 4, 5, 6. Okay, so we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All right, so that's 18. And then the 2 bonds that it makes would be its electrons. All right, it would be its electrons. So the box up top here, which would be the 4th s orbital, all right, gets empty, or it's empty. Okay, so this is 3s. Oh, sorry, that's wrong. Let's actually start from the bottom. This is 1s. This is the 2s, second s orbital. We've got 2p x, 2p y, 2p z. We've got 3s here, then 3 px, 3p y, and 3p z, and then we've got obviously the 4s, which is empty over there, or the 4th level. Okay, and that's your up-bar diagram for 4.4.1. Okay, for 4.4.2, which is the last of this 18-mark question, is write down the chemical symbols of the particles found in the calcium chloride crystal. Right, the chemical symbols now in the crystal lattice. All right, this is obviously the ions found. Okay, now we know that calcium is a Ca2+ ion, and in the chloride we know that is Cl- in ionic form. All right, we just did an off-bar diagram for the calcium ion, which is over here, Ca2+, and the chlorine ion is Cl-, okay, showing that the calcium 2+ makes 2 bonds, of course, and the chlorine minus makes 1. Okay, so that's the chemical symbols of the particles found in the calcium chloride crystal lattice. All right, cool. That's question 4. All right, I think we still have time for question 5. Okay, now question 5, still sticking with some of those ions there. The first ionization energy and electron affinity of period 3 elements are shown in the table below. Okay, so we got period 3, so sodium, magnesium, aluminium. So if we got our periodic table quickly, we go find period 3. Okay, find sodium. So we got sodium, magnesium, aluminium, blah blah blah. So period is row. Okay, period is row. So yeah, there's the page. Period is a row, so we're dealing with those, the row, 3rd row of the periodic table. All right, cool. Let's pull up my screen here quickly. Okay, cool. Now we are given their first ionization energy in kilojoules as well as the electron affinity. Okay, now they're asked to explain the difference between ionization energy and electron affinity. Now I'm not sure if we've actually gone through these terms yet, so what I'm going to do is I'm rather going to wait to go through this section a little bit later on, and I'll rather skip out question 5 rather of this paper and get to something that I know we have done. I don't remember doing this electron affinity and ionization energy. Maybe it was a while back that I don't remember doing it in our syllabus for this year, so I don't want to cover it now. Okay. As well as, yeah, for 5.2. So I'll rather just skip out on that and maybe just go to question 6. Okay. Okay, guys, I'll just do that quickly. Obviously, when I go through some of the topics one individually, and I do see that we did cover it, then what I'll do is I'll just hop back to this question and we'll attempt it. But I'll skip this one out for now. Question 6 does look like something we've done. Magnesium ribbon burns in oxygen with a light white flame to produce a white solid magnesium oxide. Name the type of chemical bonding found in the magnesium ribbon as well as magnesium oxide. Now that I know we can do. Okay. Well, first of all, magnesium ribbon is basically, we know magnesium is a metal. Okay, so magnesium ribbon is a solid form, so we know that for 6.1.1 it must be a metallic bond. And for 6.1.2 they ask for the type of bond in magnesium oxide. That's definitely ionic. That's an ionic bond. Okay. For 6.2, is the reaction between magnesium ribbon and oxygen a physical or chemical change? Let's give a reason for our answer. Okay. Well, in the physical change, remember when water changed phase to water vapor, we were still left with the same substance, which was sugar, an original substance that we began with. Okay. But here, when we burn in magnesium ribbon and oxygen, we actually do form a new substance. So we know it is a chemical change. Okay, why? Because when we do that, a new substance is produced, and that's called magnesium oxide. Hence, that's why we get that bright white flame. A new substance is formed. So whenever there's a new substance that is formed in a reaction, we know it's a chemical change. However, if there's no new substance formed, we therefore know that that is only a physical change. 6.3 says write down a balanced equation for the reaction between magnesium and oxygen. That's all good. So that's just Mg plus O2, and that should just give us MgO. Okay, now we need to balance it. You don't do this. You keep the same color pen. I'm changing color so we can see easy. So we know we got 2 oxygens here, and here we only got 1. So let's balance our oxygen. So we've got 2 oxygens and 2 oxygens, but our magnesiums are unbalanced. We've got 2 here and only 1, so we need to put a 2 in front here to make sure we get double magnesium as well. And there our equation is balanced. That was quite a simple one. So let's go 6.4 is our final question here. It says, use the law of conservation of mass to show that mass is conserved during the reaction in question 6.3. Okay, well, conserved means that whatever the mass of our reactants must equal the mass of our products. Okay, so we find our periodic table. Let's find out what is the mass of the atomic mass or relative atomic mass of magnesium and oxygen. Now, oxygen, it should be 16. All right, which is fine over there, but magnesium is 24. Okay, cool. So let's actually go back here. Let's see, that's question 7. No, we're on question 6. So let's just scroll down here. Okay, cool. So question 6.4, we use the equation 2 times 24 plus 2 times 16. All right, should equal 2 times 16 plus 24, or 24 plus 16. So 2 times 24 is, let me see, 48. Yeah, that should be 48 plus 32. And here we've got 16 plus 24. 16 plus 24 should give me 40. We've got 2 times 40. Okay, so to narrow it down, 48 plus 82 is 80. And 2 times 40 is also 80. Therefore, mass is conserved. Okay, what we began with is what we ended up with. Okay, in other words, there's no difference in the masses of our reactants and products. The masses of our reactants equals the mass of our products. Hence, mass is definitely conserved. Good for us. Okay, and that was question 6. Alright, creators, let's jump to question 9. Alright, question 9. Hydrogen H2 gas and nitrogen N2 gas react to form ammonia gas. The reaction takes place as represented by the following equation. Okay, N2 gas plus H2 gas gives us NH3. Okay, but if we balance the equation, we end up with N2 plus 3H2 gives us 2NH3. Okay, so of course they ask us to define something. So for question 9, There we go. Let's just bring this all the way up to the top. Define the term 1 mole. Okay, something we more recently have done. Okay, 1 mole is the amount of substance having the same number of particles as there are atoms in 12 grams of carbon 12, which is the carbon 12 atom. Okay, so if it has the same number of particles as there are atoms in the 12 gram of carbon 12, then we've got ourselves 1 mole of a substance. 9.1.2 of the reaction that we just looked at. How many moles of ammonia will be produced if 1 mole, how many moles of ammonia will be produced from 1 mole of hydrogen gas? Okay, so let's have a look here. That is definitely, so we got to take, so 1 mole of nitrogen plus 3 moles of hydrogen gives us 2 moles of ammonia. So we've got to take, it's about 2 out of 3, which is going to equal about 0.67 mole. Okay, which is the amount of moles of ammonia that will be produced from 1 mole of hydrogen. Okay, obviously this fraction narrows it down to 1. Okay, dividing everything by 3. So, because if we divide 3 here I think that obviously gives us 1, so we've got to divide here by 2 divided by 3 as well. So 1 mole of hydrogen will produce 0.67 moles of ammonia, and then vice versa. Okay, so 3 moles of hydrogen produces, reacted with 1 mole of nitrogen produces 2 moles of ammonia. 9.1.3 says initially 10 cubic centimeters of nitrogen and 24 cubic centimeters of hydrogen are mixed in a container. Okay, which makes it about 34 cubic centimeters of the mixture entirely. The temperature and pressure remain constant. That's lovely. Calculate the volume of the gas. Volume of gas that will remain in the container after the reaction is completed, and that's for 4 marks. Okay, so there's a big one right here. Okay, let's scroll all the way down so we can have more space, and let's work at this. Okay, so the volume of nitrogen to the volume of hydrogen to the volume of ammonia, alright, is in the mole ratio of 1:3:2. Okay, so the number or the volume of nitrogen gas that reacted, okay, is clearly with a third of the volume of H2 gas, right? Well, because that would make sense, because to get the 3 down to 1, you got to divide it by 3. So divide everything by 3, you have 1/3 is to 1 is to 2/3. Okay, so in other words, we can clearly see that 1 is a third of 3. All right, because 1 plus 1 plus 1 is 3. Okay, so the volume of nitrogen that reacted is about a third of hydrogen gas. Also, a third times 3 equals 1, and we see nitrogen is in the mole ratio of 1. Okay, so they told us in the question, thank you, the computer froze there, that initially 10 cubic centimeters of nitrogen and 24 cubic centimeters of hydrogen are mixed together. So a third times 24, all right, will give you about 8, all right, and this is definitely cubic centimeters. Okay, if you want it to be in decimeters cubed, we basically just divide it by 1,000. So 8 divided by 1,000, that'll give us about 8 times 10 to the negative 3 decimeters cubed. Okay, now initially 10 cubic centimeters was mixed with 8, right? Okay, now question is clearly in cubic centimeters, so we can't, what's the word? We can't we can't just change the decimeters cube unless we convert. Okay, so that's 8 cubic centimeters there, which was the amount of the nitrogen that reacted. So if we come back to that question, to the top here, so the volume of N2 that remains, okay, unreacted, is obviously 10 minus 8, which is equal to 2 cubic centimeters, or 2 times 10 to the negative 3 decimeters cubed. Okay. Now, of course, the question again was calculate the volume of gas that will remain in the container after the reaction is completed. Okay. So, the volume of gas that will remain. So, let's have a look here quickly. So, let me just see something quickly. 2 over 3 times. Okay. So, all of the nitrogen, all of the hydrogen obviously reacted. Okay. 2 stayed behind. Okay. And after the volume of gas that remains, so we've got to take the volume of NH3, which is equal to 2,3 of H2. So 2 over 3 times 24 will give us 16 cubic centimeters. So therefore, the volume of gas that remains, because remember they're all in gas phase, is equal to 2 plus 16, because there's still a bit of nitrogen gas that is reacted, and plus the volume of the product that formed is 16 cubic centimeters. So that gives us about 18 cubic centimeters of gas. We work in cubic centimeters because it was just a little bit easier, because they gave everything to us in cubic centimeters, so we'll just stay with cubic centimeters. Okay, makes sense. Okay, so that was that question. Okay, now they say in another experiment, 80 grams of hydrogen reacts with nitrogen to form ammonia. Calculate the number of moles that reacted. Okay, this is a bit of a nicer question than the question of old. Okay, because now we can just use normal mole calculations. Okay. So, let's see, do we have space here? Ah, no good. Let's use these. Okay, 9.1.4. Okay, well, let's use the formula. N is equal to mass divided by molar mass. Alright, mass divided by molar mass. Okay, cool. Let's use that. And we know that they say 80 grams was the mass of hydrogen. So we'll say 80 grams. And obviously hydrogen gas, it's a molar mass of 2, 1 plus 1. So we know that the number of moles here of the hydrogen gas is 40 moles, which is 40 mole. Alright, 40 mole, which is the number of moles of hydrogen gas that is reacted. 9.1.5, the volume of nitrogen of gas used at STP. 9.1.5. Okay, well, at STP, the volume of nitrogen gas, N2 gas, is going to equal to, of course, that they're in the same mole ratio because it's the same reaction. Because here they just said in another experiment, 80 grams of hydrogen reacts with nitrogen gas to form ammonia. It's the same reaction, just they gave it to us a bit differently here. It's still a third of the amount of moles of nitrogen of hydrogen, 1 over 3, multiplied by the volume at STP, which is 22,4 decimeters cubed, and we get the volume of nitrogen gas used at STP, which is roughly about 298,67 decimeters cubed. Alright, 9.2 is a big question here. 9.2 for 5 marks says, when 200 grams of lead, Pb, which is the symbol on the symbol for the element on the periodic table, combines with oxygen, 239 grams of a certain oxide of lead is formed. Use the calculation to determine the formula of the oxide of lead. Well, that must be, judging from when lead reacts with oxygen, must have lead, possibly either lead oxide or lead dioxide. Okay, because it says a certain oxide. Okay, so let's probably just have a look and see by calculation. So they say 207 grams of lead is used. When it combines with oxygen, the total mass is 239. So let's first have a look at the mass of oxygen, which should be equal to the amount of grams, total grams of the oxide, lead combined with oxygen, minus just that of the lead. And we should get that the amount in grams of oxygen, the mass of oxygen, is about 32 grams. Let's have a look at the amount of moles of lead. So, mole, lead has a mass of 207 grams, but also has a molar mass of 207, which gives me just 1 mole of lead. It's reacting here. Number of moles of oxygen, mass divided by molar mass, which should be 32, divided by 16. It's the molar mass of oxygen. That should give me 2 mole. So my mole ratio of lead to oxygen is 1:2. Therefore, my substance or molecular formula, all right, of this certain oxide of lead is Pb, 1 for lead, O2. And my question is complete. And that, great tens, is all we got planned for tonight. This is quite a long tutorial. We skipped out a few questions, but it's about an hour long. So thank you so much for joining me on this paper, 2015 paper. It's an old paper, but it's good to go through the things of old so we can see what was tested then before we just focus on just the newer stuff all the time. But let's go. I hope this tutorial helps in how to answer some certain questions and what to start thinking of for when we actually prepare for this year's Term 4 exams. Please don't forget to like and comment on this video as well as subscribe to our channel, and we'll catch you in the next tutorial.